Share the screen. So today we are getting into exponential models and their functions. So we will be seeing how exponentials look at some applications, and we'll also learn about a number you guys may not have seen before, and that is the number 8. So if you notice throughout your time in math, very rarely do we use vowels as variables. And if you may have noticed, the letters E and I don't seem to get used too much in math as variables. It's because we actually designate them as numbers. I, again, we learned last chapter, or we're fresh on last chapter, I is the square root of -1, whereas E is an irrational number that happens in nature. So a lot of times when we start examining patterns in nature, we see this number E fall out of it. Just like when we examine a circle, pi keeps showing up because if we take the circumference divided by the diameter every single time it's pi, with certain parts of aspects of nature, E ends up the same way. E is approximately 2.71828. And again, you don't need to memorize that exact value. We have calculators, and oftentimes we'll just use a calculator around the number E, but that is its approximate value. Again, being irrational, just like pi, it's only approximate because this decimal goes on forever without repeating or showing a pattern. What we're talking about today are transcendental functions, and or not just today, sorry, this unit. These are basically just a fancy way of saying are exponential and logarithmic functions. So we'll talk about logs starting on Thursday. Logs basically help get variables out of exponents. So a polynomial functions and rational functions are an example of what we call algebraic functions. As we had just said, exponential functions and logarithmic functions are considered I just need to see the word right now again, tongue-tied. Transcendental functions. Don't know why I need to just see the spelling to say that word right today. So exponential functions with a base of a are denoted by f of x is equal to a to x, where a is greater than 0, a is not equal to 1, and x is any real number. So exponential functions, the variable is in the exponent. So anytime I have some number to the power x or 2x or whatever, that's going to be an exponential function. Okay, use a calculator to evaluate 5 to the 3/5 power. 5 to the 3/5 power is going to be incredibly difficult to calculate by hand. It is basically asking you to cube 5, which would be 125, but then you need to find the 5th root of 125, which is saying, hey, what number times itself 5 times will get us to 125. You're not figuring that out very easily without a calculator, so that's what we're going to do. Oh, put this back there. There we go. So we're just going to type this in. Let me go projector mode. I'm going to do 5 then go to the power, and inside the power, I'm just going to do 3 divided by 5. Notice how that basically looks, how that was written out already. They wrote it slightly different looking than this, but it's the same general idea. So all we have to do is type that into the calculator. That's it. And look, this is how we're going to do all these problems like this. There's not going to be any like, well, this is how we'll do it by hand. No, just grab the calculator and evaluate it using the calculator. So that gave me 5 to the 3/5 is equal to, again, that was 2.6. 265. So typically I like you to go either 3 or 4 decimal places. This way I can see that, again, calculating this by hand would be a pain. All we had to do is put it in the calculator. So graphs of exponential functions. If a is greater than 1, the function is increasing. Assuming the, if a is greater than 1 and the exponent is positive, it is increasing over the domain. However, if you have a is greater than 1 and it's negative, it is decreasing as we move left to right. So that negative will make it a decreasing graph. The positive will make it an increasing graph. Let's just quickly look at that like so. If I said 3 to the x, that's increasing. If I say 3 to the negative x, whoop, thought that was a new line. Sorry about that, guys. 3 to the negative x, that blue graph we now see as a decreasing graph. So the domain will always be all real numbers, and the range is y is greater than 0. So when we look back at these, either of them, you notice it appears they have an asymptote of the x-axis. It never seems to cross the x-axis. It's just an asymptote. So I'm just going to say, hey, anything greater than 0 is my range. The intercept, if we go back to this, let's just look at the one that's increasing, is the point 0, 1. That is our y-intercept by default. But if I did something like a +2, it would shift it up 2. And again, that horizontal asymptote, I already talked about that, y equals 0. These do have a horizontal asymptote there. Sketch this graph. So again, when I talk about asymptotes, you guys did an amazing job graphing with asymptotes last unit. Please make sure that you include that dashed line of the asymptote. And just like you did last chapter, do not cross the asymptote. Just use it as a guideline. So here with this, since it's negative, I know this is decreasing. I know it has a y-intercept right here. And actually, that just happened to be what I had put for this function here. So we can confirm that y-intercept is 0, -1. You could find some other values there if you wish. I'm not going to worry too much about that, but I'm going to draw a nice paying her because it's 3 to the negative x. So this is decreasing or decaying. Was a little off on that. Let me go again. There you go. And that's it. Sometimes they might have like a +2, that means just shift the whole thing up 2. If it's like +2 sitting on the end, you know, all those shifts we learned in chapter 1 still apply. Right now, not seeing any questions, and based on who I'm seeing physically in front of me, I think we're ready to go on. So, the natural exponential function, and this is where natural logs are going to come into play next week I'm hitting natural logs, not hitting it this week. On Thursday, we're going to hit regular logs. On Monday next week, we're going to hit natural logs. Natural logs all revolve around e. So a natural exponential function is just e to the x. Remember, we're now considering e a number. And look, if you type the letter e into Desmos, it is not going to assume you're trying to make a variable or a slider or anything like that. It's assuming you're talking about the number. So use the calculator to evaluate e to the 3/5. So this is purely in the calculator. I can start. I don't see E right here, but if you hit A, B, C on the keyboard, you can hit E. And notice, it's already started to give us that decimal for E. By just typing the letter E, you can do it on the keyboard, or you can just type the letter E on your keyboard yourself. And that's to the 3/5. Come on, to the bottom of that. There we go. And look, this is all calculator work here. 1.8221. That's it. All we did was type that into the calculator. $1.8221. Again, I'm not going to expect you to be able to like, oh, you need to approximate that in your head. No, just grab the calculator, tell me what it is. Okay, again, just like the last one, for e to the x, the domain is all real numbers still. The range is y is greater than 0 because we have that asymptote of the x-axis still. And the only intercept is the y-intercept, which is 0, 1. Again, we can look at that very quickly and confirm that all with Desmos. E to the x. Now, actually, I want to look at it compared to 3 to the x. You notice it's actually, okay, there we go. We're starting to see a little more of a gap towards the top here. E to the x and 3 to the x are very similar. E would round up if we round it up to the nearest whole number to 3. So it makes sense that those graphs look pretty similar. Again, my y-intercept, 0, 1. And again, all that behavior is similar to those other ones that we looked at. The number e can be approximated by the expression 1 plus 1 over x to the x for very large values of x. So that's what we're going to very, very quickly look at. Let's look at that graph. 1 plus 1 over x all to the x. So this graph looks really weird. Let me turn this one off. But as I start to zoom out, I notice it levels off. I start running my finger along here. I'm at almost 2.7 now, but the further and further I zoom out, still in the 2.7 range. I zoom way out, so now I'm doing big numbers. It wants to stabilize around 2.718, which if we recall, that's E. So again, that was just merely a fact for you. You do not have to have that memorized or know this. This is just an interesting fact for you. You will not be tested on this. I promise you that. Okay, now let's talk about applications of exponentials. This is a very real world example of exponentials that unless something changes greatly about how we work, our finances in this country and around the world, this is something that is going to be part of your life in one form or the other. And that is the idea of interest, whether you're paying interest or receiving interest on your money, interest will be a part of your life in some way. So after T years, the balance A in an account given a principal, a starting amount of this. So here are our two functions. If we have compounding interest, we know the amount is equal to the principal, your investment, times the quantity 1 plus R, where R is our rate. So like if we're earning 2% interest, that'd be 0.02 over N. N is the number of times it's compounded. So if it's compounded monthly, that would be 12. If it's compounded quarterly, that would be 4. If it's compounded weekly, that'd be 52. If it's compounded daily, that'd be 365, all to the T times N. Now, one thing that happens in the world is the idea of continuous interest. So continuously compounding interest follows the following formula. Amount is equal to principal times E to the RT. So the idea of continually compounding interest says the entire time it's sitting there, it's just occurring, it's just gaining that interest. It's just accruing interest the entire time instead of taking snapshots at, okay, I'm just going to wait every month. I'm going to do it. No, it's saying this is happening all the time. Now, those calculations may be run continuously, but they might not post the interest all the time, constantly updating. But a lot of places will do interest in this sort of way. So we're going to look at the difference between investing. Find the amount in account after 10 years if $60 or $6,000 is invested at a rate of 7%. So we're going to see the difference between if I get monthly interest versus continuous compound interest. We're not going to see a huge difference between the numbers, but you will notice one is larger than the other. So here with this, regardless of it, I know my principal is $60,000. I know my time is 10 years. And I know my rate is 7%, which I'm actually going to write as 0.07. Remember, whenever you have a percentage, you need to write it as a decimal in order to use it in there. Now, for part A, we are going to work with our compounding interest and set the n value to 12. So for part A, it's all a matter of just plugging in here. Amount is equal to my principal, investing $60,000 times 1 plus I earned 7% interest for the whole year. That gets divided among 12 interest payments. Okay, so then it's times time of 10 years times n. We're getting those 12 there. Look, this here is a pain to calculate by hand. Quite frankly, this decimal is going to be like rather small. And then to do that to the 120th power is going to be a pain to even start to attempt to calculate by hand. So we're doing this all by calculator. So I'm just going to type it in just how I wrote it out. So that's 60,000 times 1 plus 0.07 divided by 12, close parentheses, and that is to the, I'll go put those in parentheses as well, 10 times 12, just to make sure that's still in there. So, hey, that's not too bad. At 7% interest in 10 years, we were able to over double our money. We went from $6,000 to $12,557.97. So this was purely putting it in the calculator. $57.97. Okay, that's what we get if we compound this monthly. I'm going to very quickly show you how we can change it in Desmos to compare. So like if I copy this, I can change the 12s to 4s. And when I change them to 4s, that means I compounded quarterly. Notice there is a difference. If I compound quarterly, I make about $50 less. Now let's look at the idea of continuous. Continuous says the entire time the money is there, it's constantly gaining interest. So my amount is equal to P, my principal, $6,000 we invested, times E to the 0.07. So our interest rate of 7% over 10 years. So again, this is just a matter of typing it in here. So $60,000 times E to the, now I like to use parentheses here because sometimes with the multiplication, it wants to move one of them out of the exponent. That's 0.07 times 10. And there we go. We get $12,000 $82.52. So here we made, let's see, that is a nice bit more. We made about another $25 over 10 years. Now, when you look at it, $25 over 10 years on an investment of $6,000 doesn't seem like much, but it does help it grow a little bit faster. If we were to look at this, let's look at a few functions together. I'm just going to use X for time. So if I do, actually I can do it this way. Copy that, and copy that. Okay, so if I change this to X, turn that off, change this one to 10 to an X. I'll make this one compounded just once a year. And then finally change this 10 to an X. I start zooming way out. Let me do it this way. X-axis, I want to go 0 to, let's just go 50 years. Y-axis can go from -1,000 to 100,000. Well, let me use different colors here. These colors got all mixed or all very similar. Okay, let's go red here. Keep that one purple. Let's go green here and blue for this last line. So we notice over 50 years, the blue line seems to grow the fastest, the green line's the slowest, but they all are pretty similar to each other, right? So that's an idea of exponentials there. Another thing I wanted to point out very quickly with exponentials is, something we've been seeing a lot of when we look at our data for the state of Delaware, along with COVID-19. We see I made a few different sort of exponential models here, but we notice with the data, it does seem to want to kind of try and fit an exponential curve. Like I said, I made some very fancy exponential models here. Oh, one of my data points is off. Let me go ahead and fix that. There we go. Again, some of these are a little fancier exponential models, but our data seems to be a pretty good fit for it. Unfortunately, a lot of times things like this, when we talk about the spread and growth of a virus or bacteria, they do tend to fit exponential models pretty well. And as we see, exponential models can grow very quickly. So this is it for today. I forgot to put the answer down here. That was here, $12,082. I think it was 62 cents. Let's double check. Oh, I just new blank graph. Takes 2 seconds to type it back in. Times e to the with 7% interest. for 10 years. Oh, 52 cents, not 62. So again, we did earn a little more money with that continuous interest. Here's our homework. 58 deals with the interest problems. The other problems are a little less challenging. Please do not forget about problem 58 on the homework. Looking at the interest, all you're going to have to do is type it into Desmos. So that is what I have for today's lesson. If you guys do have questions, please make sure to reach out. Again, this is being recorded, so that will be available to you as well.